In this example, we have a pipe assembly, and we're looking for the support reactions at the smooth journal bearing A, B, and C. So as before, if the XYZ axis are not given, we need to set up the XY and Z axis. But in this problem, it's already given. We already have the XY and Z axis. And then we're going to draw the free body diagram of the pipe assembly, meaning we need to remove those supports, the smooth journal bearings at A, B, and C, but only leave the reactions on the free body diagram. Here we mentioned in last class that if those journal bearings are used in sequence or in series and properly aligned, we only need to consider the force reactions. So force only. The moment condition is satisfied automatically by the assembly, by the geometry of the pipe. So we don't have to consider the moment support at each moment reaction at each support, only force. So for the force reactions, it will be either in the x direction, y direction, or z direction. So in that case, when we write the equilibrium equations, I'm gonna use the scalar equations, because again, all the forces are pointing to x or y or z directions. There's no arbitrary directions. So it's very simple to gather the forces in each direction directly. Because of that, there's no need to use the vector formulation. Scalar formulation is simpler. And then we're going to apply the scalar equations of equilibrium to solve for the unknown forces. So let's see how to write the steps down. First, let's draw the free body diagram of this 3D rigid body, the pipe assembly. So we need to identify the support reactions at the journal bearing A, B, and C. Okay, based on the direction X, Y, and Z, at bearing A, this pipe cannot move along the Z direction. Therefore, there must be a support reaction. We call it AZ, pointing to the positive Z direction. Again, those directions, when we draw the free body diagram, will be assumptions. We assume it is pointing to this positive Z direction. And then in another direction is Y direction. The Y direction, the pipe cannot move as well. So I'm going to draw positive. So unknown force, I assume is pointing to the positive Y direction. And it can move in the along the X direction, so there's no support in the X direction. Now let's move on to the bearing B at point B. Point B as well, it doesn't move up and down along the along the Z direction. So there must be a BZ in the Y direction, in the Z direction. And another direction is the X direction. So I have a force reaction along the X direction, which is BX. This pipe can move axially along the Y direction, in this case at point B, therefore there's no support reaction in the Y direction. And same idea for the C at point C, it cannot move in the Y direction, so there is a CY, and it cannot move in the Z direction. So I'm going to draw it here, which is CZ. Okay. Now we have 6 unknown forces, and we all know that for a 3D rigid body problem, we have 6 independent equilibrium equations. So seems like we have enough equations to solve all of the unknowns. So before start writing the equations, I usually put a list of the forces in given directions, because I want to know which direction has the minimum number of unknowns. Then I will write equilibrium equations in that direction. Maybe if there's only one unknown force in a given direction, I can solve that force directly with the equilibrium equation in that direction. So let's take a look. In the x direction, we actually only have one force, which is the bx, or one unknown force, which is the bx. That means if I write the equilibrium equation fx equal to 0, I can solve bx directly. And now in the y direction, the unknowns are ay and cy. Then in the z direction, the unknowns are az, bz, and cz. So there are 3 unknown forces along the z direction. And keep in mind, we have 6 independent scalar equations for our 3D rigid body equilibrium problem. So those are the 6 equations. I just put it here for your information. But the order doesn't matter. You don't have to start with sigma or the sum of x equal to 0 and then sum of y, right? You don't have to follow that order. We want to choose the equation that has the least number of unknowns. We can solve that value directly. So again, the order of the equations doesn't matter. And the reason why I put those unknown forces in each direction is to help me choose which equation I'm going to start with. Alright, so let's start with, since in the x direction there's only one unknown force, right? So the first equation I'm going to choose will be sum of fx equal to 0. And since we're not going to use those equations in order, so it's important for you to label your equations. To keep in mind, we only have 6 equations, independent equations. Alright, so my first equation will just give me the answer for b of x, which must be 0. So I put a check here, means bx is now solved. You can also put a number on your free body diagram to remind you that this value now becomes a known value or a given value. And now let's choose the second equation. To choose the second equation, well, it seems like in the z direction I have 3 unknowns. The most number of unknowns is in the z direction. So if I use the moment of the z, so we can check this equation is already used, the moment about the z-axis, then I will eliminate az, bz, and cz in my equation. Because if the line of action of the force is parallel to a direction, then the moment is 0. So az, bz, and cz is parallel to the z-axis, so there's no moment about z-axis, or moment is 0 about z-axis. So the second equation I'm going to choose is the moment about z-axis equals to 0. So az has no moment about the z-axis, bz and cz has no moment about z-axis, and also ay, since this ay passed through the origin of the xyz axis, or the line of action will intercept with the z-axis, so ay also has 0 moment about the z-axis. Now, what else can we find out? Oh, bx is 0 already, so bx actually can circle it out. We can just cross it out, and we don't have to consider it for any force or moment equilibrium equations. Now the only force that left will be the cy. That means on the moment equation about z-axis, cy is the only force that causes moment about the z-axis. So in that case, we don't even need to figure out the moment arm for cy, because it's 0 anyways, right? Cy times d z moment arm of the cy force to the z-axis, that must be 0. So this will give us the answer for cy. So cy must also be 0. Okay, so we check cy, which we already know, and put cy equal to 0 on the free body diagram and cross this one out, and then it will not affect our other free body, other equilibrium equations because it's a 0 value. And for the rest of the equations, we probably just need to use them in order now, since I don't see anything too special for now. Okay, so let's start with sum of y equals 0. Well, actually, this sum of y equals 0 is also special because now we only have one y force left because cy is already 0. Now we only have a y. That's the only force left. A y equal to 0. So, we don't have to do anything else. We already have the value for cy now. Or ay. Ay is 0, check it, and cross it. The next equation, let's write the sum of fz equal to 0. And in this equation, we have 3 unknowns, and we have 3 left. Az plus bz plus cz minus 450 equals to 0. Okay, we don't have any other equations to help us solve any of those unknowns, so we need to keep going to solve our, to figure out other equations. So equation number 5, we are going to choose will be the moment about the x-axis. For moment about the x-axis, AZ, again, because it's passed through the origin, so it doesn't have any moment about any axis. So it will be out of the equation. AY 0 is out of the equation. BX is 0. BZ is in the z direction, and we need to find the perpendicular direction or distance from BZ to the x-axis. So X, Y, and Z, 3 axes are perpendicular to each other. So the perpendicular distance between 2 lines will be, this line is perpendicular to both x and z direction. So it must be along the y direction. Let me move this ruler to the position. Hard to control here. So the distance is along the y direction. Now we figured out the moment arm is 0.6 meter, and use the right hand rule to figure out the direction of the moment. It's pointing to the positive x direction. Therefore, this moment about the x-axis is positive, and we will have BZ times 0.6 meter. And the next will be the 450 Newton. Same idea. The moment arm of this 450 Newton is along the y direction as well, from the y to the from x-axis to the z, to the 450. Actually, it's here. Line of action. And it's pointing to the opposite direction of the BZ, so the moment is a negative. We can also figure that out with the right hand rule, and the moment arm is 1.2 meter. And next, we will have CZ, because CZ also has a moment about the x-axis. And for the CZ is pointing up, then the moment pointing to the positive x direction, moment arm is 1.2 meter. And those are all the forces that cause moment about the x-axis. And this should be 0. Now simplify this equation. I have BZ plus 2CZ equal to 900 Newton. And we need one more equation to solve 3 unknowns. So the last equation I'm going to write will be the moment about the y-axis. So number 6, moment about the y-axis equals to 0. And for this, again, AZ doesn't have moment about that because it passed through the origin. And BX doesn't have moment because it's 0. Then we have BZ. We need to calculate moment about y-axis. And then for 50 Newton, there's a moment about the y-axis. Then there is CZ. So that means we can write another equation about BZ and CZ. So moment arm of BZ about y-axis is along the x direction, and it should be 0.6. Same idea for 450 Newton. It's also the same magnitude. 6.6 meter is along the x direction, and for the CZ is along the x direction, but it's longer. So it's 0.6 plus 0.4. which is 1 meter. Now we can write the equation. We will have negative this time BZ times 0.6 meter plus 450 Newton times 0.6 meter minus CZ times 0.4 plus 0.6 meter. Equals to 0. Simplify the equation. We'll have CZ plus 0.6 BZ equals to 270 Newton. So from equation 5 and equation 6, we can solve BZ and CZ directly. So use the substitution is probably the simplest way to solve this systematic equations. So we can write CZ in terms of BZ and substitute into equation 5. So we'll have BZ plus 2 times 220 minus 0.6 BZ equals to 900 Newton. And now BZ will be solved from this equation. That's the only unknown force here, which is negative 1800 Newton. And then substitute it back into the CZ formula. We can solve CZ, which is 1350 Newton. Now substitute BZ and CZ into equation 4. We can solve for AZ, and AZ is 450 minus BZ minus CZ, which is 900 Newton. And now we have all of the forces solved. AZ, BZ, CZ, AZ, BZ, CZ. And AX, BX equals 0, CY equals 0, AY equals 0, and AZ is 900 Newton, BZ is negative 1800 Newton, and CZ is 1350 Newton. And again, the negative sign only means the actual force is acting in the opposite direction of the assumption. So assume BZ is pointing to the positive z direction, but in reality, this BZ, the bearing should push the pipe down. So the force should be pointing downwards instead of upward. So it's negative upward means positive downwards. In this example, we are given the uniform plate, which has a weight of 500-pound force. So it's not showing the weight here, it just said this plate has a weight. So for the problem that doesn't mention a weight of the, for example, the pipe or the beam, that means we can ignore the weight. We can neglect the weight of the structure. But if the weight is given, apparently we have to consider the weight. So the weight will be located at the geometry center or the centroid. So we have just this rectangular plate. The weight will be just in the center of this plate. W, which is 500-pound force. And we're looking for the tension in each of the supporting cables. Here we have 3 cables only. At the origin there's no cable. So we just have 3 cables at B, let's call it TB, and C, TC, and A, TA. So we have 3 unknowns. Again, the first step is to draw the XYZ axis if it's not given, but in this problem is already given. So we can skip, move to the second step, draw the free body diagram of the plate. So here we already have this rough sketch of this free body diagram. We have 2 given forces. One is 500-pound weight, one is applied force 200-pound force, and 3 unknown forces. Write the force using scalar equations, and then I'm going to write scalar equations of equilibrium to solve for the unknown forces. Okay, let's write down the steps. First, draw the free body diagram, identify the support reactions exerted by the cables, and again we have just 3 unknowns. We know for our 3D rigid body equilibrium problem, we can write 6 equilibrium equations in total. But since we only need 3 unknowns, seems like we don't need 6 equations. So let's see which equation we're going to use. So since all the forces are directing in the z direction, so there's no x direction force, and there's no y direction force. So we can eliminate 2 equations already. And also, since all the forces are in the z direction, so the moment about the z-axis will also be 0. So now we only have 3 equations left. Also, we mentioned there are 3 unknown forces and 3 equations. We have enough equations to solve for the unknowns. So you have to write all 3 equations. So let's start from the first one. Sum of fx equals to 0. Or no, sum of fz equal to 0. We have TA plus TB plus TC equals to the 2 forces pointing to the negative z direction, which is 200 plus 500, which is 700-pound force. So this is the equation 1. Second equation, let's write moment about the x-axis. First, we recognize TB, this force pass through or intercepts with the x-axis, so there's no moment about x-axis. And the rest of the forces all will cause moment about the x-axis. And since all the forces are directing in the z direction, we are looking for the distance between the z direction and x direction. So the distance must be along the y direction, because y is perpendicular to both x and z axis. First, TC has a moment arm of 3 feet and its positive rotational effect. And TA also is positive and also has the 3 feet. That's the perpendicular distance again between the line of action of the force and the x-axis. So that distance is along the y direction. And the two given forces, well, because those two forces are in the opposite direction as the TC and TA, so they will create a negative rotational effect. It's the opposite rotation as the TA and TC. So it's negative. Let's do the 500-pound force first. 500 pound, and the direction or the distance is half of the width, which is 3/2, 1.5 feet. And for the 200-pound force is applied to the edge of the board or of the plate, so it's 3 feet. And those are all the forces cause moment about the x-axis, and it should be equal to 0. And we can simplify this equation. From this equation, we can find the relation between TA and TC. TA plus TC equals to 450-pound force. So that's our second equation. This is the first equation. And actually, combine the first and second, we can solve TB already, right? Because TA plus TC is 450, and then plus TB is 700. So we can solve it, but let's leave it at the end to solve it. Let's write down all of the equations first. Moment about the y-axis is 0. Similar idea, since this TA intercepts with y-axis, so the moment is 0 about y-axis, and all the other forces directing in the z direction, so they will cause moment about the y-axis, and the moment arm is along the x direction. Along x direction. Okay. Use right-hand rule to identify the direction of rotation for the moment. So first at TB, we extend the forefingers from the origin along this green line, the moment arm line, to the force, and then curve forefingers in the direction of the force. So your palm will be facing up, and then your thumb will point into the negative y direction. So that means it's a negative rotation based on your XYZ axis. And TB times the moment arm is 4 feet. And same idea for TC, since TB and TC all in the same kind of sense, pointing up. So you'll also have a negative moment about the y-axis, and the given forces, 500-pound force will be positive, and moment arm is 2 feet, and plus 200-pound force, the moment arm is 2 feet as well. Oh, sorry, the 500, yes, it's 2 feet. Okay, because the 200-pound force applied to the edge, but in the middle of the edge, which is 0. And now we can simplify this equation. TB plus TC equals to 350-pound force. And this is equation 3. So now we can use equation 1, subtract equation 3. We can solve for TA, which is 350-pound force. And then equation 1, subtract equation 2, we can solve for TB, which is 250-pound force. And now for TC, we can substitute TB to the 3, equation number 3. From equation 3, we can solve TC, which is 100-pound force. And these are the answer for this problem.